So I will give you a little bit of timeline how I came to balanced SSFP and non-balanced SSFP. Also my time when I worked together with Jürgen, and I'm still using SSFP, and maybe some outlooks where I see where SSFP is going. So actually I studied physics here in Freiburg. I was also born in the Stuttgart gegend where Jürgen is coming from and Gerhard Laub, and then went to Freiburg and did my thesis with Josef Hohnerkamp on inverse problems of image processing. So we had some synthetic images, we make them blurry and try to reconstruct them with inverse problems and regularization and all those things. And at the end I asked Josef Hohnerkamp, well, I would like to work on real data. And then he said, well, there's somebody in the clinics, he's doing images. And that was actually the first time I met Jürgen in person. And he was working on this 2 Tesla system, and he acquired projections basically. So radially sampled MR data, 200, 300 projections. I took the projections and I made the reconstruction. I couldn't find anymore my diploma thesis, so otherwise I would have taken a picture. So I don't know where it is, but I have a master thesis, I guess. And well, this was my first contact with magnetic resonance. I did not understand at all how it works actually. And then I moved to the University of Basel, to Joachim Selig. Maybe somebody know Joachim Selig. He was really famous in carbon-13 spectroscopy in vivo, glycogen measurements and neurotransmitters. And that was one part. He was doing NMR research, and the other part was cell membrane research, basically. And somebody told me that could be interesting. I visited him, and yeah, maybe Switzerland, you can earn a lot of money and so on. And he asked me, what do you want to do? And I said, let's try the cell membranes. They look interesting. And he said, no, you are a physicist. You go down to the MR center. You are doing MR. So it was not my decision to go into MR. And then finally, I had my MR thesis was on stochastic case-based trajectories. This is the invention of compressed sensing, actually. No, it was completely, it was just regridding, and I tried to reconstruct. So I had different phantoms, 4 phantoms with different chemical shifts, and came up with this trajectory. And what is really interesting is, I mean, my supervisor was actually Joachim Selig, and here in this publication it was Jürgen Hennig, the last author. He was kind of flexible. I mean, Joachim Selig never told me what I should do in my thesis. He had a certain program, so I just started to learn MR and came up with these trajectories. And actually, my very first paper, that I had in 1995, is a single author paper. He said, no, I don't understand this. And this was, well, try to design B1 sensitive and selective RF pulses by means of stochastic. Today it's artificial intelligence, but I really run the stochastic optimization on the scanner, so the scanner was optimizing the RF pulse, not the computer. Then I was still a PhD student. We did some titration of bold, so I used EPI sequences. The stochastic sequence was also a single-shot sequence, and we infused iron particles, and at some point we could invert the positive bold effect to a negative blood volume effect. And then I met this person, probably not everybody know, Oliver Haidt. I was postdoc still at University of Basel, and Oliver was, I think it was a double appointment, Siemens Healthcare and University of Bern, where he did not his PhD, his MD. He's very proud that he is a medical doctor, not a PhD. And well, we did a lot of crazy things. So this was without ethical permission. So we breathed these CF4, completely inert gas. And I think worldwide, we produced the first human 1911 lung images. We submitted it to RSNA. It was rejected. I don't know why. But this was actually the first time where I got in contact with this FE2D. So this is, at that time it was called the FISP sequence. Oliver told me, well, you know, T1 over T2, that's the best sequence that you can. So we used the sequence. I didn't understand why this is a good sequence. And then, well, of course, it's a funny thing. So it's published 1986, same time when Flash was published by Frahm and Haase. So this is Oppelt, Graumann, and is Daimling not an author? No, he is not an author. With really high slew rates, rectangular gradients. And what is also funny, it's a little bit similar to the sensitive point method that was published by Hinshaw in 1976, where he basically had a very inhomogeneous magnetic field, and only one point was homogeneous, and at that point he ran the balanced steady state sequence and got 1 point, and then he had to shift the phantom or something like that. Then I wanted to understand this sequence. So how does this work? Why is it T1 over T2? So Flash is T1 weighted. And well, yeah, I made some Bloch simulation, excitation, and then a read gradient. And then if you wait very long, then it's actually really easy, because this experiment is just the same as this experiment. You start from full equilibrium magnetization and scan K-space, but this is of course very slow, so let's make it faster. And then, of course, again, you can apply the Bloch simulation. You start with Z magnetization, and then what I couldn't really understand, this is the magnetization before the next RF pulse. It's not zero, it's looking like this, like transverse, longitudinal magnetization, everything. Then after that pulse, it's tilted, and then after the gradient, it gets even more complicated. And I couldn't understand how such a distribution of spins produces echoes, and what amplitude do these echoes have. And finally, at the end, it gets even worse, and I couldn't really understand how that works. And it was not explained in the Flash publication at that time. So I tried this Flash experiment, actually. I took the timing, which is in the patent and in the publication, implemented this on the sequence system, and this was the result. And then I thought something is wrong here, and looked up the publication, and yeah, well, they also have these stripes here, so I'm doing it right, actually. And but it was not clear to me what's actually going on. And then, of course, I read the 2 papers from Jürgen about the echoes, how to generate, destroy, and use, something like that. And I did a similar paper much later, of course, on Flash sequences, or basically gradient echo sequences. And well, the phase graph is more or less the same. You don't have refocusing pulses, but only excitation pulses. And then it became a little bit more clear, the FISP and PSIF and blah, blah. And then I also a little bit better understand how the balanced SSFP sequence works. Then after my postdoc, by the way, that's what I also wanted to show. So both publications, Flash and FISP at that time, are from '86. And then a couple of days ago, I looked up when the patents were filed, and this is only 6 months apart, actually. I thought this is actually much, much later, but in terms of patent, it's very close, at least the German file of the patent. Well, then I went about nearly 4 years to Jürgen's lab after my postdoc as a research assistant, and did my habilitation. That's does not exist, only in Switzerland, Germany, Austria, maybe, also with Jürgen Hennig. And I signed my contract, and then I got a second contract from Jürgen. So you can see Jürgen signed here. And development and application of gradient echo sequences is prohibited in my lab. So that was really a problem, because of course, I mean, rare was developed, and hyper echoes and so on. Well, then and the reason is when we were sitting at a scanner, at some point you said to me, well, this is non-refocused Fudelkram, model, whatever. And that's why then I continued to work, Oliver Speck already showed this, on the hyper echoes. I had once a week, we had measuring time at the Siemens Sonata, I think, 2 or 3 hours where we together, I mean, of course, it's completely Jürgen's idea, but maybe we together implemented the sequence. I also measured some echoes along this echo train, and because I had some experience with gradient echoes, I also did some simulations, how such a hyper echo works. So these are the, not sure, 4 or 5 first flip angles somewhere here, and then at a certain point, there's the central 180-degree pulse. I think this was. And then it's kind of more and more disentangled until you have a pure spin echo after the hyper echo. You cannot only apply this to spins, you can also apply these hyper echoes and Bloch equations to images, which I did here, and that also works. Now it works. So it's the same equation, but not applied to spins, but to a whole image, and then after. Sorry, Jürgen. But I did not do the simulations for these presentations. They are basically 15 years old, but I never showed them actually. And then at some point, it should go back. Yeah, the eye is coming back. Yeah. This, by the way, also works, hyper gradient echo, is because it's a very universal approach. So you can also run a FISP sequence here, central 180, and then you can fully refocus 2 gradient echo sequences. And then I worked a little bit more in the night on the balanced SSFP sequence, and then came up, well, it was kind of funny if this is a spin echo or gradient echo sequence, and in some cases it forms an echo here in the middle of the 2 excitation pulses. That can also be shown in oil and water phantom, where you can have, depending where you are in the passband, you can have opposite phases or equal phases of oil and water. And yeah, we published together a balanced SSFP sequence. And from this point, I did a lot of try to investigate much more properties of balanced SSFP. For example, this one here that was presented in Glasgow. If you run a flash sequence, it just doesn't matter how you sample k-space. It can be linear, it can be zigzag, or it can be even randomly. But if you do this with balanced SSFP, it completely fails, which is kind of unlogic. I mean, it's just both flash and SSFP have balanced phase encoding gradients, but you cannot do random encoding. And the reason basically for this is the small eddy currents that are produced if you make large jumps in the k-space. For example, if you go line by line, therefore it's better to make one line here, and then you get rid of these eddy currents that really disturb the very sensitive steady state of SSFP. This is the first 3D cardiac image that we did on a volunteer who could hold his breath for 40 heartbeats, actually, which is a lot. So the images that Michael showed are, this is fully sampled, no special sparse sampling reconstruction, with a very short TR SSFP. And then I had a presentation also in Glasgow where I used this kind of spiral CT acquisition, so projections that at the same time move in that direction, also with SSFP that was never published. Then on the transient phase, so what happens in the beginning after preparation, how does the signal decay to the steady state? Also Carl Gunter did a lot in this direction. This is important if you want to quantify. With magnetization prepared SSFP, where you measure in the early phase how this influences the signal. And that's an image that was presented in Toronto ISMRM, and I think there we were at the Niagara Falls with a big car. And then that was together with Mark Ladd. Another application, elastography, because it's very easy to disturb the steady state. So we had this alternating steady state elastography where you could very sensitive measure these mechanical waves in a phantom, much more sensitive than with gradient echoes, but also much more unstable. And these are all examples. I mean, that's all new, but it was never used or implemented in a commercial sequence. But it was just interesting to see how easily and you can disturb the steady state and make use of this. This was actually presented in Miami. Here's Heiner Kolim, who was CEO, I think, at that time. And this is, I went back to Basel in 2002. This is probably a work that, in my view, is really important, that analyzes the signal change in inhomogeneous magnetic fields with diffusion. This is important for functional imaging. So this is the well-known Weisskopf plot where he shows the signal change as a function of the vessel size in the brain for spin echo and gradient echo. And spin echoes are not that sensitive for larger vessels. And the funny thing, the same happens with SSFP. So in a way, another proof that it is at least partially a spin echo sequence is because it more behaves like this spin echo as a function of the vessel diameter. Then also MT was possible. I will jump around this. No, this was David Feinberg, actually, I think, and Jürgen and Oliver in Toronto again. And then in 2011, I moved to Tübingen University and Max Planck Institute. So I'm about 10 years now here, where we have this 9.4 Tesla system. Of course, we started with functional imaging based on gradient echo sequences. I think, Philip, you have acquired this image. So without any post-processing, it's possible to see the bold effect. So this draining vein that gets dark and bright with right side finger tapping. That's probably not possible at 3T, but at 9.4, the contrast is so strong that you don't need any post-processing. And well, I also tried bold SSFP with bold imaging with SSFP. This is based on this 2001 paper. We had a meeting, I think it was in Kyoto, with Michael Deinming and Mark Heike, and somebody of us came up with the idea, well, SSFP is so sensitive to everything, why not putting parts of the brain into the stop band, and then if you have some local frequency changes, which is induced by functional imaging, at least intravascular, about 5 Hertz at 1.5 Tesla, then it should be possible, and it was possible. That was actually done in Freiburg, this work. And I dared to do this at 9.4 Tesla, which also works fine, which is much higher signal change. But this is not measured in the stop band. This is now passband SSFP. And here also we did simulations and comparisons of the response of different sequence types, gradient echo, spin echo as a function of the vessel diameter. And here again, the simulated on an artificial on a real network measured with 1 micrometer resolution optically in a mice, and then used this for Monte Carlo simulations. And depending on flip angles and repetition times, it's also here, balanced SSFP is more similar to spin echoes. You can also do something with asymmetry, look if it's exchange or structure within the phantom. We also started a little bit with neural networks to estimate from the SSFP profile. So these are phase-cycled images, and then you get the SSFP profile, which depends on T1, T2, and a lot of other things. And we had a ground truth and then trained these nets in order to get quantitative T1, T2 fractional anisotropy images from these SSFP profiles. So a lot of different things are somewhere encoded in this steady state sequence. And finally, this is a project with the University of Stuttgart, with Jens Anders. He was able to integrate a complete spectrometer into a CMOS chip. So here on the top, you can see a very small coil that's 300 micrometers. And then you have an LNA and mixer, and so low frequency is going out somewhere here. And it has also a, well, that's not really a power amplifier, maybe a milliwatt amplifier, so you can transmit and receive. And we did an animal experiment, a bold experiment with our 14.1 Tesla Bruker system. And we could, so here from 0 to 6 was the 4-pore stimulation. And after a lot of averages, we could get this noisy signal. So this was basically pulse and acquire, no gradients, because that's a very small region. We just took everything that was visible from the coil. But this was a flash type sequence, so it was very strongly T1 weighted, and just a couple of weeks ago we implement. It's a little bit tricky because you really have to get all the phases and steady states correct, and this one here is driven by own electronics, the magnet is driven by Bruker, and you have to synchronize everything. And then eventually you can end up with a balanced SSFP signal, no gradients, nothing. I called it infinite FID, so only RF pulses and then the full steady state signal, and we also made a functional experiment. Faster, 3 milliseconds TR, much better signal to noise ratio, but it's a little bit tricky to synchronize all the signals to get this infinite FID signal. So also works at 14 Tesla, and finally, I looked up a little bit more details what Michael Daimling, no, it's not me, Arnulf Orpot Graumann, and so what they wrote. And they have that's actually the introduction. We have developed a new sequence, blah, blah, and is therefore well suited for getting with low magnetic field strengths. And that's the brain image that they got at, I think that's a Siemens system, 0.23. It's not a Freemax, I guess. And already in this paper, 86, they emphasized that low fields are beneficial, and we currently started a collaboration with Andrew Webb and try to see what is possible at 50 millitesla, actually. Yeah, and I think I'm more or less at the end of the talk. It's a simple sequence, and because it's simple, it's sensitive to everything, and yeah, I also did something else, not only balanced SSFP, and thanks to these contributors. Thanks a lot.